So your lesson for 2.5 is going to be broken up into multiple parts. It's a long lesson. And we are going to be using that reference page, the yellow card. You're going to have that out the entire time during the lesson, the entire time you're practicing tonight, and the entire time you're testing. The goal is to not need the yellow card once you get to mastery, but for now, whatever, we're new. So, graphing rational functions. There is a lot of really scary looking notation here. This slide is not in your notes. This is from your textbook. And it talks about what a rational function is. So a rational function would be a polynomial divided by another polynomial. Well, we've seen rational functions before. Like on your test, a couple tests ago, you had something like this. And it said, tell me the domain of this function. And what you guys knew to do was, oh, I can't divide by 0. So you took your denominator and you said that your denominator can't be 0, and then you figured out what the problem was, and that was how you told me domain. Well, guess what? That was just kind of prepping you for today. It's the same thing. We're going to talk about some new vocab words, new to some, not new to others. Vertical asymptotes and horizontal asymptotes on our graph. We're not going to do limit notation. You don't need to worry about that. And then we're going to discuss how you find other things like X-Intercepts and Y-Intercepts, and then eventually graph. All right, so on your notes, this is the top of your notes, and it has a lot of information here. And Mrs. Hoffbauer put stars and smiley faces next to things. I guess that tells you something. So you have a rational function where a of x is in the numerator and b of x is in the denominator. And then if there are no common factors, n is the degree of the numerator and m is the degree of the denominator. So this is a whole lot of fancy notation. Let's kind of translate this for us. So, first thing it says, I don't know why this doesn't match with your yellow card, but on your yellow card, step 1 says what? To always factor P and Q first. So step 1 on every single question is going to be factor everything. You must factor everything you can. Then, it's going to ask you about domain. We'll come back to the concept of domain in a moment, but we already know what domain is for a rational function. It's where our denominator can't be 0. We'll come back. Vertical asymptotes would be a discontinuity caused by a vertical asymptote would be when your denominator equals 0. I want you to write a note here by vertical asymptotes though. These are lines. And they are in the form x equals whatever. So when I say give me the equation of the vertical asymptote, if you just write down 4, that's not a vertical asymptote. I need the equation of the line. For a horizontal asymptote, again, these are lines. So they're going to be in the form y equals whatever. We're going to discuss this in a minute about whether it's bottom heavy, equal weight, or top heavy, and then we'll discuss what that means. But notice those same words I think are on your yellow card. If you guys look at number 7 on the yellow card, it goes through a little top heavy, bottom heavy, equal weight thing. We'll discuss that on an example coming up. And then there's a concept down here called oblique asymptotes. Another word for oblique is slant. So if you ever are looking at a rational function and it seems to be having a weird little asymptote, but it's like diagonal instead of up and down or side to side, that's called an oblique asymptote. We have to find those when we have what's called a top-heavy fraction. X-intercepts. If there are any x-intercepts, it occurs at the real zeros of a of x. So to translate that for normal humans, we're going to say set your numerator equal to 0. A of x, remember, was the top of the rational function in this example. Okay, y-intercepts. If they exist, it's what happens when x equals 0. So if you want like little kids speak for that, you can write down plug in x equals 0. So these last two concepts, those are things we technically already knew. When you're trying to find an x-intercept of a function, it's where your function equals 0. So for a fraction, in order for a fraction to come out to 0, that means the top of the fraction has to be 0. A y-intercept is where it crosses the y-axis, which is where x equals 0. So it makes sense to say you're going to plug in x equals 0. But these things should be pretty new and pretty unusual for you guys. Honors Algebra 2 kids, did you graph these before? A little bit? Like really slight amount in Honors Algebra 2, like vertical asymptotes? Okay. Regular Algebra 2 kids, never seen it. College Algebra kids, I think you're doing it right now, actually, in College Algebra, if you're in it right now. Yeah? Okay. We'll see if we match. All right, so here's an example of comparing the degrees to the polynomial's numerator versus denominator. So horizontal asymptotes, in your notes, if you could you write down this? A horizontal asymptote is really just asking about end behavior. And we don't talk too much about end behavior because we keep having this really pretty template for end behavior. But think about what end behavior is asking. It is asking what happens when your x's either get super duper duper small and negative or super duper duper big and positive. So I want you to think about this for a minute. This purple function, you don't have to write this down, just kind of look at it. I don't like negative numbers, so let's go positive. Give me a really big positive number. Okay, something with a lot of zeros.
100.
Bigger.
1,000.
Bigger. 2 million. Oh my gosh, all right. So what would happen if I plugged in 2 million into this purple function? Well, I'd get 2,000,006 over... okay. So when you square 2 million, you get 4 followed by 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you're going to subtract 6 million plus 2. Now, I know this sounds like a weird comment, but in comparison to this number, aren't these like nothing? Like, I've never thought I'd say the words 2 million is nothing, but I don't even know what that number is. 4 followed by 12 zeros? Like, I don't know. We'd have to Google that because I have no idea. Is it a Googleplex? Wouldn't that be magical? I don't know. I don't even know what a Googleplex is. So either way, what's happening here, guys, is you're taking a relatively small number and dividing it by a gigantic number. What happens to fractions when you have huge denominators? Like 1 over 100. 1 over 1,000, 1 over 1,000,000. You start getting teeny, 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 tiny, little tiny decimals. What number is it trying to approach when you keep dividing by bigger and bigger and bigger numbers? It's approaching 0. So when you have what's called a bottom-heavy rational fraction, or rational polynomial. No, not the rational equation. There we go. Bottom-heavy. So you have more x's in the denominator. The degree is higher in the denominator. You're going to end up with a horizontal asymptote of y equals 0 every single time. So let's look at what happens when you plug in 2 million into this red function. Okay, great. All right, so you have 2 million squared, 4 million, times 2. No, that's not right. 2 million squared is 4 followed by a bunch of zeros times 2. There. So it's 8 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Guys, I'm not going to bother with this part of the function because in comparison to the number I just wrote down, it's nothing. And then we're dividing it by 2 million squared, which would be 2 followed by 12 zeros. Okay. And then what's happening is all this negligible stuff I don't even care about. But look at all these 12 zeros are going to knock each other out. What do you have left? Oh, guys, this was 4, wasn't it? What do you have left? 2. Look at the original problem. Coefficients. So if you're plugging in giganto numbers and you have the same degree over the same degree, those giganto numbers are just going to knock each other out, and all you're going to be left with is the line y equals whatever your coefficients are for your lead terms. Now look what happens when it's top heavy. Okay, apparently I can't do mental math with 2 million, but you're going to end up with 4 followed by 12 zeros times 5. So that's like 20 followed by 12 zeros. Pretend I wrote down 12 zeros. Divided by what, comparatively speaking, is a very tiny number. Now, was 2 million the biggest number you could have given me? No, what if we plugged in 10 trillion? I don't even want to think about that. That's like huge, right? So the bigger your numbers get, the more out of control your numerator was getting. Well, guys, what are you approaching if your numbers just keep getting bigger and bigger and bigger and bigger? You're going to infinity. So you're not really going anywhere but beyond. So what happens when you have a top-heavy fraction, like we have here, is there's actually no horizontal asymptote. Bad news, though, that means you do have what's called an oblique asymptote. We'll probably have to save that conversation for tomorrow because I think we're going to run out of time today, but we will come back to that concept. All right, this is kind of what's on your reference sheet, and we're going to go through these in order. For the sake of time, though, I'm going to try to stick to your notes as much as possible. This one I think is done in your notes, although for some reason it's done in the wrong order, so sorry. All right, on our yellow card, step 1 of your yellow card says factor everything. So I look at my polynomials. My numerator and denominator are not factorable. So step 1, check. Step 2 says the domain of all real numbers except those that make the denominator equal to 0. Because we know from our work with rationals before that your denominator can't be 0. That means there's some type of discontinuity. So what they did was, we did cheater's domain. X cannot be -3. See how they got that? Domain means denominator can't be 0. I don't need you guys to do interval notation for domain. You're good at that. We can move on in life from interval notation. Now, let's talk about vertical asymptotes. On my card, it doesn't show up for a while, guys, but if I look down to number 4, it says if x minus b is a factor, but not a factor at the numerator. In other words, there's no canceling. We'll come back to that. That thing down there is also going to be your vertical asymptote. Now notice, what they just wrote down was x equals -3. That is a line. When you're giving me a vertical asymptote, you have to give me a vertical lines equation. Now, I noticed these two things matched. Well, that kind of makes sense, guys. If you have what's called a vertical asymptote, what that means is right here, there's kind of like a weird invisible fence, and something happens, and it disrupts the domain. So a vertical asymptote is a type of discontinuity that will break up your domain. That's why they're matching right now. Not the only type of discontinuity, however. All right, the next thing they'd want me to look at is horizontal asymptote. That's that new thing. So when I look at the original problem, I have to decide if what we have is top heavy, bottom heavy, or equal weight. So look at the degrees of the numerator versus the degree of the denominator. That one is equal weight. So looking at my little yellow card, if the degrees are the same, it says that your horizontal asymptote is at y equals the coefficients. So that's why they have y equals 2. Again, this is a line. It's the equation, this time, of a horizontal line. Y equals 2. Alright, so this one's a little strange, because like I said, it's going out of order. If you guys back up to number 5 on your yellow card, in order to find an X-intercept, when you look at your original problem, and you've factored and you've looked for canceling, we'll talk about canceling later. If nothing is canceling, for X-intercepts, you want to find out when the numerator equals 0. So you set your numerator equal to 0 and you solve. Alright guys, what happens when you take this numerator and set it equal to 0? You get 1/2. But what I need from you guys is the understanding that an X-intercept is an ordered pair. An X-intercept is, in this case, it's the ordered pair 1/2, 0. X-intercepts, zeros of your function, they're all the same thing. And then my favorite one to find is the y-intercept. A y-intercept is where your function crosses the y-axis, but by definition, it is where you're going to, quote-unquote, plug in x equals 0. This is why this is my favorite question. When you go up to a standard form set of polynomials, if you were to plug in 0 for all your x's, that first term becomes 0, and then you have a -1. And then in the denominator, you have a 0 plus 3. So all you're really looking at are the constant terms. So what does that reduce to? -1/3. So again, pre-calc, you have to understand that this is an ordered pair. Y-intercepts are in the form 0, in this case, -1/3. Have you noticed I haven't grabbed my calculator once? Because you're going to have to do this on Friday's no calculator test, okay? I know people in the back can't see. Can you see now? So here's where I wouldn't ask you to move on a no calculator test. on your homework, you're going to find all these things for me, and then you're going to have to go graph them. So you're going to graph everything you just found. Now they already did it for you, but notice. We had a vertical asymptote at x equals -3. At some point we found a horizontal asymptote at y equals 2. I always mark those with highlighters when I'm like graphing on my notes. The other things that we found were an x-intercept at 1/2, 0. Now they didn't really do a great job with, look what they did. They counted by 2s. How annoying. Alright, so there's an x-intercept at 1/2, and there's a y-intercept apparently down here at -1/3. Totally can see that. And then from here, I would never expect you guys to know the shape of the graph. Like, I don't even know the shape of the graph sometimes. So here's where you would grab your calculator and you type your function into y1. But can I give you guys a word of caution? Your calculator reads horizontal fractions, not vertical. So you're going to have to put 2x minus 1 in a set of parentheses, and then you're going to divide it by the fraction, the polynomial x plus 3. So just be aware that, yeah, you will at some point on your homework have to type something in your calculator, so make sure your entire numerator and your entire denominator is set in parentheses. So are we clear for the no calculator test? I will not have you graph a thing, but you're going to have to find all those things. All right, this one is on your notes and not done for you finally. Okay, so what I would like to do on this question, I want to follow the yellow card in exact order that it appears so we can get a little muscle memory here. So step 1 says to always factor everything. Well, the factoring fairy came by and already factored it for you, so done. Okay, step 2 says the domain is the set of all x values except for those that make the denominator equal to 0. So look at your denominator and think about telling me that your denominator can't be 0. I see 2 problems. What are they? X can't be 0. And x can't be, solve this one for me, 6. So I could be a jerk and make you write in interval notation, but I'm not gonna, because that's terrible. We have enough stuff to do today. Okay, step 3 on my card, it says, look for factors that are going to cancel. That's basically the summary of what 3 and 4 say. So, guys, your factor in the numerator is x plus 2. And I don't see that anywhere else in the problem, so you're not going to have any canceling. So I'm moving on to step 4. Step 4 says, now that you've looked for canceling and holes, we'll come back to the idea about a hole. Find your vertical asymptotes. So your vertical asymptotes are lines that create discontinuities because the denominator would be undefined if it was 0. So your first vertical asymptote is at x equals 0. Make sure that's written as a line. And then your other vertical asymptote is x equals 6. Again, make sure that's written as a vertical line. Sometimes kids don't understand the difference between domain and vertical asymptotes. There is a very big difference. The main one being asymptotes are lines. And then the other issue is we're about to encounter something called a hole. A hole is also a discontinuity. So they're not always going to match up, the vertical asymptotes and the domain. All right, we're on step, what, 5 now? 5 says to find your zeros or x-intercepts. Those are interchangeable concepts, right? Zeros are x-intercepts. So to find our zeros, we're supposed to set the numerator equal to 0. Okie dokie. So x plus 2 equals 0 would give me x equals -2. But you're better than that, PreCalc. Give me an ordered pair. Zeros are in the ordered pair form of x comma 0. Where are we at? Step 6. Y-intercept. Y-intercept is where you, I need a color, here we go. Y-intercept is where you plug in x equals 0. So I'm going to go back up to my function. And I'm going to plug in zeros for all my x's. So I have 0 plus 2 over 0 times 0 minus 6. Now think about this, guys. You're going to get 2 over 0. What is the number 2 divided by 0? It's an undefined expression. So do you have a y-intercept if you can't define it? No, we do not. So you're going to say none. There's no y-intercept in this problem. And then finally, let's talk about the horizontal asymptotes. Now, a bit of a bummer. They had it already factored for me, and horizontal asymptote inspection is really easiest if everything's in standard form. So I'm just going to throw these together real quick. I'm going to call this x plus 2 over x squared minus 6x. That's the same thing as the original problem, just unfactored. So now look at your degrees and compare the degree of the numerator over the degree of the denominator. Are we looking at a top-heavy, bottom-heavy, or equal weight fraction? This one's bottom-heavy. So what does your card say about a rational expression that is bottom-heavy? Your horizontal asymptote is at y equals 0. Again, guys, remember, this is a line. It's a horizontal line at y equals 0. So on your no calc test, those are all things I might have you find without a calculator. Now, on your homework, you're going to take it one step further and you're actually going to graph it. So first thing I do when I'm graphing these is I take my highlighter, if I have one, or a colored pen, and I draw in all the asymptotes. So y equals 0 has an asymptote. X equals 0 has an asymptote. And these are counting by 2, so be careful, but x equals 6 is a vertical asymptote. I mean, let's be honest, my graphs are never great, so I need all the help I can get. Okay, we did find a couple more things, guys. You found that there was an x-intercept at -2, 0. So right here, it's going to cross the x-axis. And then we also found that there were no y-intercepts, so I'm not going to be able to graph a y-intercept because I don't have one. And this is where I would stop thinking and I'd grab my calculator. So in order to save us a little time, I'm just going to tell you guys what this one looks like. This branch over here, this does something kind of weird. It scoots down along the asymptote, it dips below the x-axis slightly, and then it comes back. And it scoots along the bottom of the x-axis. There is no reason for you to know off the top of your head it does that. I wouldn't expect you to know that. But one thing I do want to make clear, because I think this is a misconception from Algebra 2, sometimes kids think asymptotes are like fences where you can't cross, and that's not what they are. Horizontal asymptotes are end behavior. So in the far ends of our graph, this little blue guy is going to kind of scoot along that asymptote forever. It's going to keep going that way. All right, over here, this branch, I only know this because I graphed it, looks something like this. And then there's this weird little horseshoe looking thing, kind of looks like a parabola, a little flatter. I don't really know exactly what it looks like, but something like this. But notice, at no point in that graphing did I cross the y-axis, because there was not a y-intercept. I will warn you, there's one on your homework. You probably won't get to it until tomorrow, because we got to finish the lesson tomorrow, but the graph is real terrible. And, you know, I didn't stand a chance graphing it, so sorry. In your notes, could you please find these questions? I think they're in the back. So on 9B at the very top, this is kind of reminiscent of the first few questions on your homework. So it's going to give you some rational equations, and then it says find the vertical and horizontal asymptotes and also the domain. So if I think about keeping my process similar, I'm going to go through all my yellow card stuff first, which it says first, is anything factorable? So look at number 1 here. Is anything factorable? This is not factorable unless you want to use i's, and I don't want to use i's. So everything is technically as factored as it's going to get. So let's talk about how we find domain. I saw on my yellow card that the domain is when you say the denominator can't be 0. Well, guys, try solving that. You would subtract the 1, and then you'd try to square root a -1. What's going to be the problem here? You're going to have imaginary numbers. Are you going to be graphing imaginary numbers? Nah. So the domain, there is no issue. There's no point where x can't be something. So what is your domain then? All real. So -infinity to infinity. Can someone hit the door, please? Thank you. And then they want to know about vertical asymptotes. Well, remember, your vertical asymptote is related to domain in this case, because it would be when my denominator equals 0 and I would solve it and find lines, but we're going to have the same issue here, guys. Are you going to be able to graph the line x equals I? No. So for vertical asymptotes, you're going to have none. And then for horizontal asymptotes, this is where you look and you compare the degrees of the numerator versus the denominator. So we have a degree 0 over a degree 2. This is bottom heavy. And when something is bottom heavy, what does that mean for your horizontal asymptote? It's at y equals 0. Make sure this is an equation, y equals 0. All right, number 2, there's nothing I can do as far as factoring. The numerator is a 2x plus 1 and the denominator is an x plus 1. Those are not the same term, so they do not cancel. So let's talk about domain. Domain would be problems with my denominator. I see one. What is it? X cannot be -1. And the reason x can't be -1 is because you have a vertical asymptote discontinuity at -1. So the equation of your vertical asymptote is x equals -1. Your horizontal asymptote would be a comparison of your lead terms here, guys. So what's the degree? Oh, they match. So you have what's called an equal weight fraction, which means your horizontal asymptote is the equation y equals, this would reduce all the way down to your lead coefficients, which are 2. Y equals 2. Alright, someone already came through and factored number 3. That was nice. So I'm looking through my factors and I notice nothing's going to cancel. In a moment we'll talk about what happens when they do cancel. So my domain, remember, would be my denominator can't be 0. So what are the 2 problems that I'm going to encounter for my domain? X can't be -1 and x can't be 2. The reason x can't be -1 or 2 is because you have 2 vertical asymptotes in this question. You have a vertical asymptote at x equals -1 and a vertical asymptote at x equals 2. Make sure these are equations. And then for horizontal asymptote, it was nice of them to factor that for me and all, but I think we kind of need to go backwards and think of this in its standard form. This is x squared plus whatever. So look at your lead terms now. You have an x over an x squared. Is that top heavy, bottom heavy, or equal weight? Bottom heavy. And when you have a bottom heavy fraction, that means your end behavior equation is y equals 0. Oh boy, fun times. So I kept throwing the word factoring out at you, we need to factor, nothing cancels, we need to factor, nothing cancels. So what happens if when you factor something does cancel? Well, we're going to skip ahead in the lesson, right here. This is on your notes, I believe. So this is an example, a generic example, of what happens when you factor a rational expression and you're going to have what's called a removable discontinuity. Okay, that's the fancy term. A removable discontinuity is very easy to see because it will remove itself from the problem through cancellation. So it is when terms cancel. The unofficial name for a removable discontinuity is a hole. And it literally is a hole in the middle of the curve. The problem is you can't see it on your graphing calculators unless you know where to look. It's tiny, right? Points don't have size, they're tiny. So you're not going to see a big circle on your graph. We're going to draw a big circle though, but it's going to be crazy big. All right. Here's what's going on, guys. When you have a removable discontinuity, like here they had x minus a, and they had another x minus a, and then they crossed them off. Well, the hole is located at x equals a. So whatever the solution was to that factor, that's the x location for the hole. All right, here we go. Finding holes. I think this is something on your yellow. All right, look at number 3 on your yellow card. It says, if x minus b is a factor of both the numerator and the denominator, there will be a hole at x equals b. Now keep reading. It says, to find the ordered pair, put that x value back into the reduced rational function. Here's what I'm talking about. this problem right here, which is totally on your notes. Look at that. So they already came through and factored it for you. And they saw through their algebra that x plus 2's would remove from the problem. So that tells us that we have a removable discontinuity, also known as a hole, at x equals -2. Well, that's great. But on your test on Friday, I'm going to ask you for the precise location of the hole. So -2 is the x value. How do we find the y? Well, you can't plug it into the original problem. Because if you plug it into the original problem, you're going to get 0 over 0, which doesn't really tell you anything. So what we're going to do then is we're going to go to what's called the reduced version. See what they have here? After they remove the discontinuity, they cross it off. This is the reduced version. Look what happens when you plug -2 into that. You get -2 minus 2 over -2 minus 4. And what is that? -4 over -6, better known as 2/3. So you can find the location, the precise location of the removable discontinuity, first by factoring to figure out where in the x value it was, and then plugging into the reduced version to find the y. So that's fun. All right, let's see if we can get through this next example. I think my hope is to get through all of example 5 and then most of example 4. That's how far I got in first hour. Let's see. All right, got your yellow sheet handy? Here we go. Oh, I'm sorry, we already did 5. Shut up, Abruzzo. Let's do number 4. So, way to start you off nice and easy. Your first job is to factor everything. Well, that numerator is not going to be a problem for you guys. You're just going to factor that. So x squared minus, what, 7x plus 3? Oh, jeez. No. X plus 7. X minus 7, x plus 3. Oh, lordy. There we go. Now, this denominator, talk about a hot mess. It's a 4-term polynomial. The only approach I know, algebraically speaking, is to try grouping. This one doesn't group nicely. I don't really want to think real hard. So if this was a homework question, I would have cheated big time. I would have graphed that polynomial, looked at the calculator, and went, where do you cross the x-axis? And that would have been how I factored it. And that's exactly what I did. So I graphed it, and I went, oh, well, turns out this dude crosses the x-axis at, where is cross? -3, -1, and +2. So I want to go write the factors as x plus 3, x, I already forgot what I said, plus 1, and x minus 2. So I didn't do any magic to factor that, guys. I just went, hello, calculator, thank you. Otherwise, I would have had to do synthetic division, and no. I vote no. Okay. So, step 1, factor, check. Step 2, talk to me about your domain. So the domain would be a listing of every single x value that's going to give you a problem, which means anything in the denominator right now. I see 3 problems. Tell me who they are. X can't be -3, -1, and 2. Now, the reason why they are problems is because they produce what are called discontinuities. They're not all vertical asymptotes. Because look carefully at that fraction, guys. What do you notice? Is there a hole? Yes, there is. Look at this. X plus 3 and x plus 3. Mathematically speaking, they would cancel each other, wouldn't they? All right, so I'm on my yellow card, and I'm looking at number 3. It says, if x minus b is a factor of both the numerator and the denominator, you have a hole to consider. So the hole is located at x equals what? -3. Thank you. All right, but this is not good enough for PreCalc. You got to find the actual ordered pair. -3 comma what is my question. All right, look at what's left here, guys. You have x minus 7 over x plus 1 times x minus 2. So if you plug in -3 into that leftover stuff, you get -3 minus 7 over -3 plus 1 times -3 minus 2. Oh boy. Negative 10 over negative 2 times negative 5, so 10. What does that reduce to? A negative 1. You just found the y value for that whole is negative 1. Okay, so we're still on step 3. We just finished step 3 on our yellow card. Step 4 says, now look at all the other factors that don't cancel and find your vertical asymptotes. So your vertical asymptotes would be what's left in your denominator. So not the part that created the whole, but the rest of it. So there's a vertical asymptote at x equals negative 1, that's a line, and x equals 2, that's another line. So guys, this is what I was warning you about. A lot of kids think domain and vertical asymptotes are the same question. They are totally different questions. They are heavily related to each other, but any discontinuity creates a domain interruption, and that includes holes. All right, where are we at? So we're on number 5 now. It says zeros or X-intercepts, whatever you want to call them. Let's go find our zeros or our X-intercepts. So that would be where you look at what's left in your numerator, so not the whole that was removed, but whatever was left, and solve that equals 0. So x minus 7 equals 0. So apparently there's an X-intercept at 7, 0. And then for my favorite one, the Y-intercept, that's where you plug in zeros for all the x's. So I'm going to go way back to the original problem that was in standard form. And I'm going to have like a whole bunch of zeros here. I need a bigger screen. All right, so I don't know what they are, but 0 plus 0 minus 21 over 0 plus 0 plus 0 minus 6. So all you're going to be left with is this negative 21 over negative 6. Guys, what does that reduce to? 7 over 2. So you have a y-intercept at 0, comma 7 over 2. If you want to write that as 3.5, you can. All right, and then finally, was this top heavy, bottom heavy, or equal weight? Bottom heavy. So your horizontal asymptote is at y equals 0. So we're going to pick up here tomorrow. We're going to actually graph this baby. You guys can get going on your homework. The only thing you can't do on your homework yet is the one that has an oblique asymptote. So the only one you guys are going to have to skip for now is number 24. You'll be able to do everything else on your homework.